really hope that this is the beginning of more and more collaborations across the two institutes. Of course, in the past, Andrea has worked a lot with people at UBC, George Savatsky. You had a lot of interaction with them. We had a lot of discussions about a number of topics, routinates, but I think we have techniques that are becoming really mature. You also have shown amazing results you can achieve with your numerical analysis and theoretical analysis. So I really hope we can come together. Another reason to come together is we also have a Max Planck UBCU Tokyo Center in Vancouver. Soon you're going to have a Max Planck Center here too. So there's even more overlap. And again, as far as the topic and focus of your center is all on ultra-fast techniques. So quantum matter, dynamics aspect of quantum matter. So I hope that we can really do more and more in the future. Today, I'd like to discuss a particular technique, which is angle resolved photon emission spectroscopy, used to look at the electronic structure of solids, but now in the time domain. The work has been done by two groups which have been working together for many years, my own and David Jones, who is also a faculty member at UBC, and who's coming from GILA and an expert in quantum optics. So it would not be possible to do the kind of work I'm going to show you soon if you didn't have really two groups working very closely together, because you do need the expertise on both sides. I'll try not to bother you with too many technical details. I'll emphasize those which are really relevant for the new opportunities that are becoming available. But please stop me on whatever I say that is not clear and is of interest to you. I'll be in particular describing three works. And in fact, the primary authors of the works are all here in the audience. So Katie, that was given a journal club Monday, and Fabio, who has not given a talk but was involved in discussion today on cuprates. And in addition to that, we also Berend, who also gave a talk, and he's a collaborator on this one, although has not been leading this work. His area is iridium oxide. So in particular, do a review of some of the results on the cuprates, so bismuth and so hole dope and electron dope cuprates, but also a new approach to determine electron phonon coupling, in particular electron phonon matrix elements, using time resolved techniques, and apply them to a system which is a rather simple one, graphite, which is then being used as a benchmark material. You see that the separation of the two is because we are using two laser sources, and I get in some of the details about this one because it's really a novel tool that we have that opens up completely new possibilities. Photon emission, this is a historical slide, goes back to the time I was a postdoc with ZX at Stanford, and basically is a technique that allows you to follow a band dispersion in a solid by removing an electrons. And in fact, by doing that, you're really probing directly the single particle spectral function. And so what you do in an experiment in the old days, we would change the relative angles between samples and analyzer and follow the dispersion of these peaks, which you can follow up to the chemical potential, where we have no more electrons, and so you can't see and follow the unoccupied part of the band dispersion. And if you go and look and beyond just the location of the peaks, you also look at the detail of the line shape, you start getting information about the self-energy. And you guys here are really experts at that. And I have to say that we have gone through the work you do, Manuel and Antoine, on all of the sorts of routine, and it's quite amazing what you have been able to do in an orbital, selective, and sensitive way on the case of transfermutinate. So I won't go into the details of this because the next step is to go and describe what can you do when you bring the time resolution to this problem, so that you now do an experiment where not only you shine a single photon on the sample to remove a single electron, but you precede that by an additional pulse, which will excite your material, basically excite a number of possible excitations in the solid, from electrons to collective nodes, and then probe the system afterward at a given delay and a variable delay over time. So time resolved photon emission in different forms. Before going into our particular cases, I'd like to show some of the examples which have really captured a lot of attention over the last few years with this technique. I'd like to start with this one, 2011. This is a case where people look at a charge density wave system. So here you have a material, and you have two different phases, the low temperature phase, the high temperature phase. And in high temperature phase, you have a rather well-defined band structure with two symmetry points which are distinct. When you go below a phase transition, a CDW type phase transition, these 2 points become equivalent, and so you start seeing folding of bands due to the CDW. Now the idea is to come in with a pulse, and so this data basically correspond to this region before the pulse comes in. You cannot read the number, but it's 0th femtosecond is when a probe and pump pulse come in together onto the sample. And so what you can see is a variation in the band structure. For one thing, you see some filling of electrons above the chemical potential, but also there is modification there, which tell you that this folding, which was seen before, has now vanished due to the melting of the CDW. So in a way,
selenium too.
This is, yeah, it's one of the selenides in this system, those family of systems. So basically, you can really follow the melting of the CW. One thing I like to take your attention to is really the energy scale. You're looking at 2 electron volts here. And the reason is, this experiment is done with a laser that allows a high temporal resolution, but doesn't have the energy bandwidth to look in a very fine way close to the chemical potential. And that is a technical challenge that we'll overcome towards the end of the talk. Another example, or another way of using this beautiful data coming from the exchange group, where basically you're doing a 2-photoemission experiment. You're looking at a topological insulator, bismuth selenium in this case. Here is a chemical potential. So with standard photoemission, you would look at electrons below, so the occupied states. But what is being done here is to excite electrons from the occupied into the unoccupied electronic structure, and then photoemitting them from there. So pretty much what you're getting is a picture or a mapping here of the unoccupied dispersion of the solid. Something that you would be able to see if you did inverse photoemission, but you don't have this kind of resolution, or if you were able to dope the system all the way up there, but you can't really. And so by using this 2-photon technique, again, one pump pulse exciting the sample and the second one probing at a certain delay, you can get a very detailed picture of the band dispersion above EF, to a point where you can see the topological surface state, the Dirac light state here, but you also see the existence of a second one, which is usually not occupied in the pristine material. Yet another way now is not just melting a CW and then mapping a band structure, but is really changing the character of a quasi-particle. This is bismuth cuprate, work done in Manzara's group, where you have a dispersion, the single dispersion for a copper-oxygen band here. And what you do, you come in at some delay with a pump, and then you probe, and you can see just from the color that something has changed here. And if you look at the detail of a spectrum taken at a given momentum here, as a function of energy, you can see it here, for instance, you can see that between the equilibrium data in black and the red one, the transient data, there is a difference. The difference is concentrated on the peak. The peak is what we would call the quasi-particle, and the area under that peak is what we usually would call the quasi-particle strength. And so what you're seeing here is that by coming in with a pump, you can really, here we talk about meltdown, you basically suppress the coherence of those quasi-particles, or at least this is the interpretation. But certainly you're doing something, now you're not just populating states above EF, you're doing something to the spectral function itself.
Can I ask you a question?
Yes.
So those different curves, those are somehow normalized to each other?
So actually, no. In the original, I asked that question when I saw this talk the first time. I was quite surprised. So the different curves are basically following the dispersion. They have not been normalized. They overlap very well over here. So to me, it was surprising because usually, like in the first slide I showed, I would call this the coherent part of a spectral function, and this the incoherent. Both of them, I would expect, should change equally if I, for instance, change my condition for photoemission in some way. And so I would have expected, if I change polarization, for instance, I would expect both of them to scale down equally because they are related to the same original excitation. What you can see here is something happens to the coherent part, which is not apparently tracked by the incoherent. So there was no renormalization.
I don't understand. Can you say again what the measurement is that a pump makes some excitation, and the result of that excitation is a decrease in strength of the coherent part of the normal quasi-particle spectrum.
Right. Now here is the difference. So you actually see that there is a depletion here, an increase there. If you look into the details, I think we may have different interpretation, and Fabio, I'm sure, would have a slightly different interpretation of what goes on. What was surprising at this stage was really to see that what looks like the amplitude of the quasi-particle is coming down.
So okay.
But it's something to be discussed, you know. If
Okay, but that's the result, is that there's a pump excitation
Yes,
which causes apparently the amplitude of the quasi-particle beat to decrease.
that's
But
right.
and that's done below TC.
This is done below TC. Correct? This is done at 20 Kelvin. And
Which
again,
was
Fabio,
In our case, it happens above, below, and above TC. We did also on 2201, where TC is pretty low. And you can still see up to
Yeah, okay.
This was optimally doping 2212, so I think it
90
was a
Kelvin.
90.
No, my question just referred to the sentence here, you know, about connection between nodal quasi-particles.
That
So
was
the
what-
superconductor has, of course, nodal quasi-particles. It's a D wave.
yeah.
And then the experiment is we go with our pump. We somehow, this harms the superconducting coherence.
Well, so
Is that just?
I don't think this was quite interpretation there. So this has been to me a very puzzling aspect.
So what goes with the pump and the coherence of the nodal quasi-particle goes down,
Yes.
the amplitude goes down.
And let me just say that this was
So-
limited to the nodal direction because with the kind of photon energy available in that system, that's all you can see. Okay, you
Right.
cannot really follow.
But I realize that this is a paper which is not directly your work, and there's
Right.
there is no independent evidence in this experiment of a change in the superconducting condensate amplitude caused by the pump.
No,
The experimental evidence is just pump reduction of nodal quantity.
that is correct.
That's what I want.
That is
Yeah,
correct.
okay.
So let me just
So these are facts we
anticipate.
can think about
The
later.
latest coming from Fabio would be that perhaps if you went in with the frequency-dependent scattering array, you may be able to reproduce this effect. So,
I'm totally not surprised by that.
okay, so, but again, this was an interesting observation done, whatever that
Yeah.
means, it was.
Yeah.
One more experiment, which is very interesting, is again from ZX's group. This is a combination now. Here is a little cartoon of two techniques, not done on the same samples, not at the same time. One uses a free electron laser generating almost 9 kiloelectron volt of X-ray in a pulse, and that you can send onto a sample together with a pump, which excites the sample. And so what you can do, then you can follow a Bragg peak in the X-ray intensity as a function of delay between the two, and you're going to see oscillations in that Bragg peak. The Bragg peak is associated in the oscillation, so the oscillations are associated with a phonon, which has to do with the motion of the selenium atoms with respect to the iron atoms along the z-axis. And so these oscillations really, if you transform them, they correspond to one particular frequency, so one particular mode being excited. At the same time, or in parallel, you can do an experiment where you shine the same pump energy, 1.5 eV, and now you probe it with a UV pulse, and you see what happens to the band structure. So it's a combined time-resolved X-ray diffraction, time-resolved photon emission on the same sample. So here now the modulation in these two plots of the bands at the gamma point, which, if you look at the frequency and so on, follow exactly the modulation of the Bragg peak in the X-ray diffraction experiment. So in other words, you're looking at some in bands below the chemical potential, you're modulating the particular mode, and as that mode is modulated, also the bands will of course change. And the conclusion of this was that of an enhancement of, a transient enhancement of electron phonon coupling. Now, one limitation of this experiment I'd like to highlight, because it's important, is all of the photon emission data is taken close to the gamma point, again because of the limit in photon energy of this photon, 6 to 7 eV usually. And if we wanted to see what happens to the superconducting gap at the zone boundary, you would need a much more energetic photon to do that, which is usually not available, but is becoming available with our source in our lab. So that would be an interesting experiment we would like to of course, do while looking at the zone boundary. So,
Sorry
yes.
for keep asking questions on the that's not your work, but so why is this 1.5 EV?
the choice,
Yeah, isn't that kind of far away from?
it is, but it's basically related to the kind of lasers that are available, so titanium sapphire lasers, so it's a convenient frequency to put on the sample. You could do like Andrea Cavalieri is doing, to go directly to terahertz into the phonon regime, but that presents its own complication.
But I mean, is it then surprising that it only excites
But-
one mode?
Well,
Or?
what,
Or
Yes, to some degree. I would say that you really have to look to see how the energy is transferred to your system, particularly to the electron system, how it goes from there to the phonon system. And there is one which is a dominating mode, the winds.
But this is a pretty ubiquitous observation, right? I mean,
Yeah.
in these experiments, usually you pump with some non-discriminating energy, and then, you know, all sorts of things happen. The electrons react to the phonons, but
And
one or two
one
phonons
phonon
emerge
wins or
coherently.
So that's sort of what happens. You know, pretty much has been shown that unless you probably go right at resonance, it's really, you know, it would always happen, and it's not even so much dependent on the specific photon energy you're using.
Correct.
Okay. So dependence on photon energy is not so obvious, but so that happens by itself, by the system, and the interactions in the system. Last one, well, this is very familiar to you because, you know, Andrea Cavalleri's work, the two system, the YBCO, and you, Antoine, have already done a lot of work with Andrea on this, the C60. So the idea of going and enhance superconductivity into a system, perhaps all the way to exhibiting signature superconductivity all the way to room temperature. Now, this is all optics, it's not photo emission. And the reason why is because, well, first of all, here is a different technologies being used in building the pump pulses, generating those pump pulses. In both cases, you really would like to probe what happens to the electronic structure away from the gamma points, so close to the zone boundary, and therefore using a very large photon energy, which has so far not been available for this kind of study. So to us, this is a very interesting study that we would like to replicate, but not looking at the time resolved reflectivity, but really looking at the time resolved for emission signal, angle resolve. With this, I'm done with the introduction. I like now to move to Fabio's work. And Fabio's work is all focused on the bilayer bismuth cuprate, so bismuth 2212. It's pretty much the same material you saw in the paper from Manzara that I was mentioning before. And as I sort of highlighted, one can do an experiment where it's some time before the pump pulse, so some negative time usually means before the pump has come in, you see a band dispersing all the way to the chemical potential. And after some delay, if you pump it, there is a change in population around that peak. And usually what you do, you show difference plots, so the pump minus the no pump signal, and then you can see a depletion of signal below EF and an increase of signal above EF. And generally, you will see traces like this, where you have a delay, an evolution of that signal as the pump arrives, increase above EF, depletion below EF. You have already seen in previous examples that you can do much more than just that. So in fact, you can go back to look at what is the definition of the photon emission intensity in terms of a spectral function, so the excitations of the single particle excitation of the system times a matrix element, which is basically the probability of removal of that electron, so transferring that electron optically from initial to final state, and an electronic distribution function, the Fermi-Dirac distribution function. So many different effects can be studied. Here, what Fabio has done is to go and look at the loss of phase coherence in the superconductor as you go pump it, and to see what happens to the spectral function there. Trying to decouple, in this case, temperature from actual intrinsic changes in the spectral function. So here is the motivation for the study. So this is a conceptual phase diagram of the cuprates, some doping, some parameter here, doping, temperature. Here is the dome, and this goes back to the Ember and Kivelson's picture of having now a superconductor with very weak phase coherence. So a dome which is defined by two parameters. One is the pairing energy, the formation of basically of Cooper pairs, the coupling between Cooper pairs, the binding, and the other one is the phase coherence those Cooper pairs will have. And the conjecture at that time was in this particular system, while on overdope side, the pairing is the defining energy scale, on the underdope side would be the phase coherence. So very weak phase coherence, and so TC is really only cross when the phase coherence is large enough. What can we disentangle these two effects? But based on temperature has been particularly challenging because everything changes. So the idea was the following. Here you have two quantities of interest. One is pairing and the other one is phase fluctuations, so fluctuations of that phase coherence. And TC is usually defined not only when the pairing is finite, but also when a certain value for phase coherence is reached, at least on the underdope side. So is it possible to do an experiment where now you come in with a pump, you excite your system, and now you look at what happens. Two things can happen. One is you're going to warm up your sample in a way, so the gap will definitely change in some way. But is it possible that perhaps the dominant effect is the change in phase coherence? And how can we tell them apart? Well, based on this model of spectral function, in fact, Andy has worked on it back in the days with Marcel Franz. So here is a spectral function now with a self-energy which takes into account the two parameters, so the superconducting gap and the phase coherence itself, or the phase fluctuations. Those would go both in the self-energy. What would the spectrum look like in the case where one is dominant or the other one is dominant? So here is the spectral function shown about the chemical potential. Keep in mind in photon emission you will only measure the unoccupied part usually, but this is simply how you define. Two peaks separated by a gap, 2 delta. Now if when you pump it, what you do, you modulate the pairing strength, so delta, well, simply the two peaks move close to each other, the gap gets smaller and nothing else changes. If on the other end, much of the action is in the gamma, so in the broadening, in the phase fluctuation, then the peak would basically stay in the same place, but they broaden out and spectral weight is transferred within the gap. So the two sort of scenarios would be gap closing versus gap filling, related to pairing being the key parameter in controlling superconductivity, or phase fluctuation in the other case. And here is the experiment. The experiment looks already surprising to some degree, even without a pump. So here is chemical binding energy. Here is the temperature, 6 Kelvin. This is your viscous sample. Then these data are measured along the node. Sorry, close to the node. Here you can see the Fermi surface of this cuprate. So you have nodal data, and here they are measured just away from the node. So the gap is large enough. It's not the largest gap, which you find at pi 0, but it's large enough to be observed. The surprising part is that not only you see a peak below EF, but you also see a peak above EF. And this is where the sensitivity of experiment and the ability of experimentalists comes in. You are basically seeing data which are measured well above the chemical potential, and you still can see the occupation of that state at this very low temperature. And this requires very high statistics, and also, so of course, Andy is surprised by this, but so this really requires very high sensitivity, very high statistics, and then you have to sort of divide off a Fermi function. This is actually not just divided off, it's a deconvolution that Fabio has done, where also resolutions are taken into account. So deconvolving the whole thing, and you can get this kind of data. Just keep in mind, there is no pump. It's not like we are heating up the sample by coming with a laser. So this is the low temperature data, and the gap is very well defined. Now the question is, you come in with a pump, what's happening next? Is it the closing or is it filling? And here are the data. You see a little bit of a change in the gap itself, but mostly the biggest change is in the filling itself. So it really is a broadening out of the peak, and the gap almost doesn't change. And if you wait for time to come back, then of course over time the system will go back to the original state. So the conclusion of this work directly is there is no gap closure, there is a filling, so the dominant parameter here in controlling superconductivity appears to be the phase coherence itself.
Okay, but wait, this is, so what I see in this experiment is that the consequence of the pump is a filling in of the density of states,
Yes.
with only a very small change in the gap.
Correct, yeah.
But is there any independent information about the effect of the pump on superconductivity?
Well, if you're asking transport type, no.
Or anything, I mean?
Well, no, basically there is not. We basically, Fabio can go and increasing the fluence until the point that you can no longer see a gap. No.
Mm-hmm.
No.
So
and this is a question that I will address with the last two slides of the talk, because really the question is, what kind of experiment can you do, on these kind of time scales?
Yeah.
Where you could probe that.
Well,
definitely.
I mean, of course, doing a direct probing of that is not so easy, but if you got optics, sigma 1, sigma 2.
Right, there's like the microwave
The
or something.
the 1 over omega term in sigma 2 being depleted would be an indication of suppression of.
I would have liked even something more,
You would like something more, I understand.
I would like something more
too, but that's.
But we would like something.
I would like something more than that.
Yeah.
But okay, you can do optics on this and see similar features presumably, but I really would like something more that I will discuss at the end of it.
Yeah, but Because one can interpret this slightly different. This is antinodal, I suppose, right?
Nodal, close to nodal.
Well, there's a gap, so it's not.
There is a gap.
So it's
It's
not
close
nodal,
to
so
nodal.
it's close to nodal.
It's not antinodal.
But
It's-
this
it's-
is, okay, fine. But so we could interpret this differently. We would say, okay, what the pump is doing is killing the superconductivity or damaging it, but we still keep a gap, as we see. So the gap is really
But-
pseudo gap,
right, so
not of superconducting origin.
So I would like to, I would basically, let me put, the kind of experiment I like to do is an experiment that allows me to tell whether I'm having pairing in momentum space or pairing in real space. Am I observing a BCS to BC crossover type situation? That is the kind of experiment I like to do. I would like to be able to distinguish between these two kind of scenarios.
Yeah.
So I fully agree with you. This is not directly an indication of superconductivity in a thermodynamic sense. Just looking at a spectral feature is changing, usually we associate it with superconductivity, but indeed it could just become very incoherent and you still retain a pseudo gap. Going forward with this, you can do a more detailed analysis in terms of this spectral function in particular, follow the delay evolution. You see that the gap is changing about 10%. That change in 10% is consistent with electronic temperature that Fabio estimates there by looking right at the node. The biggest change is in the gamma, and interesting is, this is what defines basically the quenching, if you like, and the recovery as well. It's really that time dependence. The simple model we put forward, well, for one thing is we have a superconductor.
Here, wait, hang on a
Yes.
second, Andrea.
Yes, sorry.
How does it depend on fluence? So my big question would be, could I have two regimes depending on the fluence? Once I just mix the phases, and second time I just really destroy the amplitude.
Possibly. So there are two fluence regimes that Fabio has explored. I'm showing you the low fluence regime. And as you go to high fluence, then you start seeing bigger changes everywhere, and eventually the gap is completely gone.
But even if you go to a fluence where you have a complete filling of the gap, almost complete filling of the gap, and the electronic temperature is similar to the one of TC, the gap anyway is reduced of 30%, while the gap is complete. But the filling is almost maximum. Then if you pump more, then the gap is completely filled, and you don't see any other variation.
So the idea here was to try to low enough that you could distinguish the two. Okay, even though there is this, what is you're lacking is this a direct measure of a superconductivity point. So going back now to the model or the interpretation, the idea you're pumping the system, you are creating a population of hot quasiparticles. Those will thermalize by interacting with bosons in your systems, and as they do, you already broke quasiparticles here. You're breaking more quasiparticles, so you're scrambling the phase coherence of this condensate, and eventually, as the thing relaxes, it goes back to itself. So the conclusion would have been, if this is a measure of superconductivity being quenched, is then really driven and controlled by phase coherence, which then confirms the role of phase coherence in the high TC phase diagram, especially the underdome. So the next part of the work we would like to do here is to continue this also as a function of doping, as we have talked today about the NCCO. And in particular here, moving towards the overdope, I'd like to see the side of the phase diagram. Interesting, if you look at the dynamics, the gamma terms, so the phase rotation terms, builds up with a certain delay of half a picosecond as compared to the arrival of the pump itself. So really this is the build-up time of the non-equilibrium ozonic population that you have. I'd like to switch now to actually what we have already been discussing a few people this morning. So this was the whole doping, right, looking at superconductivity. What about another phenomenon which is really important, which is a pseudo gap, which Antoine has already brought up before, and in particular from the electron dope cuprate case. So here is the simplest picture of the Fermi surface of the cuprate, one large hole-like Fermi surface centered around the pi, so the corner of the zone. And in a situation where antiferromagnetism is well established, you now have a reduced Brillouin zone electronically, and so this particular direction represents a plane about which the surface can be folded. So this is a so-called pi folding, and here when the two cross, that's where you have the hot spots with increased scattering and so on. In the electron dope cuprates, this is being seen experimentally quite well in terms of a suppression of spectral weight over here. And the question we'd like to ask is, what happens to the system when antiferromagnetism is not so robust anymore? And so what Fabio has done, took a sample that was basically optimally doped, so away from the very robust antiferromagnetism, look at the Fermi surface. This is a simulation done here. Look in particular here and see, can we still see signs of a pseudo gap? Can we track it in temperature? And can we relate this to the correlation length, magnetic correlation length? So these are the data. These have been again measured with a 6 eV laser. So we're sort of bound close to the nodal direction, not all the way to the antinode. And what Fabio's done is really, well, in addition to take a Fermi surface, is compare data taken close to the nodal direction with close to the hotspot itself. Let me go directly into the dynamics of the signal. Then, for people who are interested, I can tell you how he extracted that. What you're seeing here is two different fluence regimes. Red is high fluence, black is low fluence. The horizontal axis is delay, and the vertical axis is the intensity in the hotspot. So it's the spectral intensity in the hotspot. If you like, if I didn't have a pseudo gap, intensity would be 1, and if the gap is a complete suppression, intensity would be 0. Any value in between is the evolution of a gap which is not complete. And what he has done here is actually quite interesting, was basically a way of using the pump to transfer energy to the electron system, and so increase the electronic temperature while not perturbing the rest of the system, and do it very efficiently and very effectively. So basically, in a matter of, say, minutes, measure the full temperature range, and then repeat. So experimentally, there are issues with the sample aging and so on, but this way of approaching the problem is very fast and very accurate. So all of these fluences and delays can be turned into now delay versus electronic temperature. Basically, at each delay, what Fabio can do is to look along the nodal direction, look at the Fermi edge, extract an effective temperature, and replot this data versus delay and electronic temperature. And then finally take the intensity that he observes per the pseudo gap and plot it, the intensity of the pseudo gap versus electronic temperature. And when he does that, the scatter plot are the data that Fabio has obtained. You see that the intensity of the pseudo gap basically, as the pseudo gap grows as a function of temperature and then saturate. The green line underneath is 1 over the spin correlation length. So basically, you have a low temperature state, which is not a long-range order antiferromagnet, has a finite correlation length, and as you go up in temperature, it gets shorter and shorter, and so what you see a diverging 1 over xi over here. And there is an interesting point, which is the one that defines T star, so the onset of the pseudo gap, and that's basically when you see that the intensity of the hotspot departs from the curve, and that's basically when the broadening is of the order of the pseudo gap itself. And so again, if you does an analysis of this of the spectral function, you would see a gamma term will become comparable to the size of the pseudo gap itself, and that's when the evolution of intensity stops. But basically, the bottom line of this experiment, you really see that the pseudo gap itself emerges as a consequence of the spin correlation, even though they're extremely long range. And so this really raises the question of how far in doping can you go? How short can the spin correlation length be, and yet still see an effect on the Fermi surface of the material? Next, I will switch to another case, which is the one of graphite. So I'm down for very strongly correlated systems. So if you have questions here, please ask me, because then there is quite a bit of a change of gear in the next case. So what I've shown so far was all work done at 6 eV. So low photon energy, you're probing close to the gamma point of whatever materials. You cannot really expand all in momentum space. And this has been so far the biggest limitation in this technique. Angular result for emission, when you use a synchrotron, you can go from, let's say, 0 to 100 and thousands of electron volts, very high energy resolution for the beam. You can map all of momentum space. You can do the same when you do resonant X-ray and things of this kind. And when you do this work with lasers, you're sort of stuck. You're transferring energy from the photon to the electron. The electron to come out of the solid has to pay about 4 to 5 eV for energy due to the work function. So when you go at 6 eV, you really have very little kinetic energy for the electron itself. So the idea here was to go at much higher photon energy and yet retain the resolutions that you need to do a proper work. So this is particular, we show work which has been led by Katie and Art Mills, and really involved David Jones' group very strongly here. The idea was, what about electron-phonon coupling? Can we use this technique now, a time domain technique, to look at electron-phonon coupling? Electron-phonon coupling obviously is very important for most materials that solid has. The two primary ones, perhaps superconductivity and the CDWs, or charge order. What can we learn about that? And so if you look at what are the different ways of determining electron-phonon coupling, of course you can do the calculations, there where ab initio calculations work. You can do scattering experiments of various kinds. Usually, you can look, when you do an experiment like that, you can follow the evolution and the coupling for a specific mode, but you lose information of the electron momentum, or it's integrated above all of them. In photon emission, often people have looked at a dispersion and deviation from the pristine dispersion with the bare dispersion due to electron-phonon coupling. This is a case of graphene that we've worked on. And there is the old machinery of using self-energy, real and imaginary part of the self-energy, to extract the coupling. But that has a couple of problems. The first problem is that when you do this, you're actually integrating overall possible modes in Q. So you're not really doing a specific state in K with a specific mode in Q. You can if you're really heavily guided from theory, but experimentally it gets really challenging. But there is other kind of problems I'd like to highlight. And here is one. This is what Katie has already used when we discussed the graphene case on Monday. So this is now for graphene. Later in the rest of the talk, I will look at graphite, and she has worked on graphite. But here, let me discuss the graphene case. So here is the lambda, so electron-phonon coupling, extracted by in a number of papers, and you can already see the spread in these values. These are as a function of the doping level for the graphene itself. And there are many reasons for all this mismatch, but certainly one clear reason is resolution effects. Apparently the cloud of this cloud of data, when interpreted taking into account resolution, can be pushed down to a value which is much closer to the DFT number. The blue data for the graphene case were obtained by Lanzara's group here in two ways. One is taking into account deviation from linearity of the band that is used to describe the Dirac point. At the same time, graphene not grown on silicon carbide, which is usually the case for most of this work in order to do photon emission, but grown on copper. So having a metal underneath where you have an electron gas that would shield correlation effects, that is the claim. In this way, you can get something that matches what DFT tells you. But you can see the challenge in this case. And this is a case where correlations are not particularly important. I like to highlight what happens to correlation when you have correlation by using the case of BISCO 2212 once again. So this is a very old data set from 2003. What this is showing is lambda is a function of doping in BISCO, so cuprates. Optimal doping is right here. If you start from overdope and you look at the normal state, you more or less see an independent behavior. But as you start looking at the superconducting state, here's what you see. And so the message of this paper is huge doping-dependent increase of the mass enhancement below TC. But huge really means that this line is approaching the value of 10. And to me, this looks really unreasonable. And I would attribute the issue here to two aspects. Anytime you do this kind of analysis of a lambda, you're assuming a bare band. You're basically imposing some behavior for the bare band. And then people, at least you have shown that you go way beyond that. But what experimentalists often do, once they have established a bare band, they write a self-energy as additive contribution from all possible terms: electron-electron scattering, electron-phonon, impurities. But of course, this is not correct. Really, you should have a well-defined Hamiltonian that contains all of your interaction. Then you would go and calculate your self-energy. And then from that, you could try to extract some quantities. So this is what happens when, in my opinion, when you look at electron-phonon coupling this way, based on, here is a dispersion, let me put a linear band through it, and look at a difference between the data and the band, and from that infer what the self-energies are. So the question then is, can we do it in the time resolved mode? And in particular, instead of looking at lambda, can we look at something more fundamental? Can we look at the matrix element square for electron phonon coupling for a specific Q? And can we possibly do it by looking then, extracting them through the electron phonon scattering time that is directly related to it? Graphite will be the sample. Graphene is still, do you have a question, John? Yeah?
This formula you integrate over K, or the formula you wrote on the yes?
This one here?
Yeah.
No. Well, we'll see later.
Okay.
Depending. The graphite will be the sample. Graphene still used as a model, just a toy model to explain the idea. So the idea would be to come in with a pump. It's again 1.5 eV, just because it's the same photon energy coming in, 1.2 in this case. Just go and populate states above the Dirac point, and then wait to see when they relax by emitting a phonon. And what it means is, if I start off with a graphene sample, which is populated up to the Dirac point, through the optical excitation, we create state above EF at about 0.6 electron volts up there, say, and then we wait. After a certain amount of time, related to the electron phonon scattering time, you would see that the population, the intensity is transferred down in discrete step, and this discrete energy difference is the photon energy, if you have the phonon energy, if you have an Einstein phonon in the problem. And then again, what you would like to do is go from this electron phonon scattering time, if you can measure it, and extract G, and then in principle you can also extract lambda once you you introduce your electronic densities. What does it take to do that? The experiment looks very trivial, but or simple, the concept, but what does it take to do that? Well, problem is graphene has, or graphite, they are the same. They have a band structure which is located really at the corner of a Brillouin zone. So just to get there kinematically and have enough cross-section, you're looking at photon energy above 20 electron volts. So you can forget about 6 eV lasers. You need photon energy, though, in the range of 100 MeV to be able to distinguish this kind of energy scale, the phonon energy scale. And as for what the scattering time is, you need scattering time or resolutions of the order of 100 femtosecond, say, or better, ideally. So what you are in need to do is develop a system that can generate those photons. And the way, usually this is done, you can take a system, amplify, go in a gas jet, and through the partial ionization of a gas, you can generate high energy photons. However, when this is done with a single pass, so a single pulse going through a gas jet, you really have to amplify your pulses so much that you lose that proper relation between the temporal characteristic of your spectrum and the energy characteristics of the bandwidth. So what it means is, effectively, you can generate up to X-rays with very high temporal resolution and extremely poor energy resolutions. Extremely poor means you wouldn't be able to look at anything like that. So here the idea was to create a cavity, and this is David Jones and our Mills group. Create a cavity which you pump with an oscillator, you store energy in that cavity, and you still have a gas jet, but now you're working with a very high repetition rate, very low peak powers, therefore you can control the temporal energy profile very well, and you're going to generate very few high energy photons or UV photons, but because the repetition rate is so high, you're going to have many of them per second, so you can do the experiment. And in fact, you're going to generate an array of harmonics, and you use an image, actually, that has been measured in the chamber, and you will go and select one, which then is sent onto the sample. And at the same time, you come in with your pump pulse, and you can do the experiment. So when you look at numbers, photon energy for this particular experiment was 25 eV, but it goes up to 40 eV if you look at the full spectrum. Resolution in time, 190. In energy, 22. Repetition rate, 60 megahertz. So all the parameters you need to do this particular experiment, and a bunch of others. So for instance, if you wanted to do Cavaleri's experiment, but look at the superconducting gap, we could do it in principle. Or if we wanted to do the same experiment ZX has done on the iron selenium, but look at the zone boundary of the gap, we could do it. So before I said you could, there are some large-scale facility where you can do this kind of work, but what are the parameters? So this is our chamber in UVC, where you have an emission chamber and 2 lasers with 6 eV and the up to 40 eV. Here is Artemis in the Rutherford lab, and here are the features that you should look at. we can so actually they can generate an amazing temporal resolution, 30 femtosecond, but then you look at energy resolution and usually it's 200 MeV or above. So often many hundreds of MeV. In our case, 190 is what we have in this particular experiment, but 22 is what we can get. So it's an order of magnitude better there. And so really for this experiment, that particular machine wouldn't work. So here are the data. These are the data that Katie has already shown. And you have data measured at the core of a Brillouin zone. Here you have the chemical potential, so electrons are below the chemical potential, and here you see the Dirac light dispersion. You don't see one side of it due to cross-sections issues. And then you start pumping, so 0 femtosecond is when pump and pulse are coincident, and well, there is a faint hint of intensity here. If you take the difference between the two, you have a depletion, the increase. Really, we would like to look at 0.6 eV/IDF, which is actually here. So the question is there a structure here? Is there a peak? Fortunately, you're not seeing very much here. And the reason is that the intensity down here is about 4 orders of magnitude less than the chemical potential. So one way to do it is integrate this data in momentum and zoom in on a single trace. So we zoom in on a single trace, which decays from here, going up this way. And on that tail, on that decay, you see structure. So we can now subtract the background and just concentrate on this structure. And then start discussing this. And so to some, this peak at 0.6 is precisely what we expected to be able to see. We see some structure that perhaps is suggestive of this phono relaxation mode. But in fact, there is more than we expected. And we also see that there is a tail, and the tail is really due to the electron-electron scattering, which is very fast, and so it's dominating. And we'll then take the intensity from this value to something which is 4 orders of magnitude higher. So to me, actually, when we see this, it was just amazing. You could see structure. I really didn't, was really surprised when you could see directly with your eyes structure in the data. So now the game is that of analyzing the structure, understanding the structure. Why all these peaks? Well, in fact, if you look at graphite, has a more complex band structure than graphene, so there is many more optical transitions which are allowed. There are in fact 4, and in this particular range, there will be 3 optical transitions you should be able to see. So we're concentrating now on 2 of them, which match exactly what you would expect here. And what we do then next is here in blue, for instance here, we show the primary peak, the strongest one, and the second one in blue, the ones that we know. And then we concentrate particularly on the red one, which does not match any of the optically loud transition, in the hope that maybe that would relate to a phonon excitation. And what you see here as a function of time is a change in delay. So here is as the pulse is coming in, and then the 2 pulses are coming closer and closer together. And the system evolves, and you see how the intensity grows and then decays again. So what we can do next is really follow as a function of time the intensity of a primary peak, let's say the 2 electronic peaks, so DTP1, where DTP stands for direct population. What you can see is they have a maximum which is coincident, which is close to the 0 delay, meaning pump and probe overlapping exactly, and then so it comes up to it and down to it with a width which relates to the width of the pulse. The question is then, what does the red structure do? And the red structure also follows that, but with a delay. Delay which is marked here by the red arrow, 42 femtoseconds. And the 42 femtoseconds is interesting not only because you can really resolve a delay, but because that peak has an energy of 165 millielectron volt, which actually matches one of the optical modes for this system. So once you have this kind of data, you can interpret that and model that in terms of rate equation. Basically means I will have an evolution for the intensity of this particular peak, which is driven by the intensity, the number of electrons which are excited there by the pump, minus the number of electrons which are then lost due to electron-electron relaxation, this tau thermalization, and minus the number of electrons which are lost due to electron-phonon scattering, tau q. So in practice, you can look at these 2 equations, and this is the intensity coming in, and this is the intensity going out. And you have the second equation, which is for the phonon peak, which gains intensity due to a relaxation process, but then loses intensity through the 2 same mechanisms, electron-phonon and electron-electron scattering. by following this, basically by modeling this data based on this equation, you actually can come up with the curves you see underneath, and not just guide to the eye, very proper analysis in terms of this equation, and then you can come up with the key numbers that we were after. Electron photon scattering time, 174 femtosecond, electron scattering 56, and then using this relation, you're now extracting the GQ square of 0.050. For now, it's just a number. So we'll go and compare two calculations to see whether these numbers make any sense. The key thing is, here you see 42 femtosecond doesn't quite relate to any of the two, and really is a balance of the two. So this delay is determined by how fast is this relaxation process, and so how fast is the intensity coming into that phonon replica peak, and how fast does the intensity leak out of it due to electron scattering in particular. And that gives you where the maximum is. Now going back to the question, John, you were asking. So what do we know about this Q? Well, for one thing, we go to the phonon dispersion for graphite. We see that you have a mode, 165 eV photon energy, and is actually the optical mode at the K point, so this particular region. And then we ask, what is this connecting? Well, this is connecting two valleys of this material from K to K prime. And so if we look at the process, we can actually go and calculate for this particular state in K, so an electron here, you're scattering through a K mode, losing this kind of energy, this amount of energy, and then you can calculate how is the electron phonon coupling going for a small variation of that Q vector of the mode all around there. And so you can do, so then the calculation is usually done for one particle in this state, going down to, with that mode, that particular mode down there. And of course, it applies to the whole ring around the dispersion. So in this case, you have a photon energy, you have a measured quantity of 0.05, and the calculated turns out to be actually very close, 0.04 for the two. So in a way, the method works extremely well. Of course, you can also see relaxation going down vertically almost through a gamma mode. In fact, if you look at electron phonon calculation that take into account all possible scattering channels to all possible states, the two modes seem to be both strong, the K mode and the gamma mode. But when you do a calculation which is all the same way, then you figure out that the coupling is only 50% of what you see from the K mode. And so in the end, we don't see the quantity in the peak, although it may be underlying some of the structure, but we are not able to pinpoint that. So finally, this comes to a comparison of the data that we had done back initially. Unfortunately, it's really hard to do comparisons for the case of graphite, and also because we are actually not working with graphite up here. We're down here where the chemical potential really is. We are working up here, so we wanted to do something that could be meaningful at this kind of density of state and extract a lambda. So we go back to the graphene case. See the data that were obtained basically by Lanzara's group with a DFT kind of estimate that was in agreement. And so the two numbers here that you get at this particular value, which is where we are, 0.6 CV above the chemical potential, are in the range of 0.034 for a lambda. And then when we calculate our lambda, is about a factor of 2 less. Okay? It's comparable, but a factor of 2 less. And this is interesting because, as I was showing before, there are two possible mechanisms for decaying here, but the one we have measured is this single one. While in this kind of analysis, you're integrated over all possible one, and so you're also looking not only at the K phonons, but also the gamma phonons, and that would explain why our number is roughly a factor of 2 of what's seen with the other approach. This basically concludes the specific experiments that were done by either Fabio or Katie. I'd like to say a few more things about future. One is, so far we have worked only with a fixed photon energy, 1.2 eV, but the idea is to go and tune this photon energy, so building a system that really could produce energies from 80 to almost 1 electron volt, and so that you can really be able to come down close to the high energy phonons for a variety of materials, or really into that range, depending on the system. So in principle, you could imagine going resonating with a particular lattice mode. So that certainly is one. But even in a case like this one, would be really interesting to scan along this unoccupied dispersion and see whether the kind of estimate we have made is how dependent it is on the specific state you're reaching and so on. It's actually interesting to look at the scattering rate for the process we were looking at in terms of, in a more realistic way, where not only we look at the coupling, but also we look at the electronic density of state, the occupation for the phonon, so the phonon population, and for the electrons. And so basically, by playing with different conditions, we could be able to play with all these different terms and see what is the effect, on the quantities that we extract. But also go to really look at what is the role and what are the key coupling concepts for some of the superconductors. That's sort of the idea. So by really try to discriminate between the role of density of state, occupation of bosonic modes, and so on. And so you can do that by playing with this, the frequencies, and also the fluence dependence of this. Finally, I'd like to go to this idea. And that goes back to, do you see a gap for the emission experiment? What does that mean? So here is a condensate. Condensate, where you have Cooper pairs, which have a very specific wave function. We usually assume them to have a total momentum k equals 0. And in a full emission experiment, like the one we have done, come in, remove one of the electrons. Of course, as you remove the electron, any information about the wave function is lost. That is completely gone. What if we could do an experiment where now you can remove both of them simultaneously so that they are simultaneously detected at two separate detectors? Well, if that was the case, in fact, you should be able to reconstruct the wave function of a coupled pair, of a coupled object, so the true many-body wave function. And so obviously there are some difficulties. You need two detectors. You need photons of the proper energy range because now you're photoemitting two detectors. And you need a strong enough coupling where you have a final probability with a single photon to emit two of those electrons. Now, let me give you an example where this really would be nice. So here is a case of a superconducting gap and a pseudo gap. So in red, as a function of Fermi surface angle, you have a nice D wave-like gap. You go above TC, and then you retain a gap at the antinode, and there's no gap close to the nodes. Well, if I had, now I'm working on this superconducting state, and if my Cooper pair is a total momentum of 0, so k and minus k is the momentum of the two electrons forming the Cooper pairs, and I do this kind of experiment, I would imagine to see, when I photoemit two particles at the same time, two electrons coming out, one with a peak at minus k and one with a peak at k. And they should be coming out in a coincidence experiment. So one photon in, two electrons out, and then you go and explore the angular distribution of those electrons, and you should find two peaks exactly there. If the pseudo gap was made of preformed pairs, you could imagine that you would have a much broader distribution, perhaps peak around the same points, but without coherence. So really, this would be the kind of scenario which I would like to see. In fact, if instead that gap and none of that, you probably would see a completely uniform distribution of intensity. And so ideally, what the kind of experiment that one could dream of is to do a coincidence experiment, see a situation of this kind, then come in with a pump, drive the system, let's say quench superconductivity, and see that this signal disappears. So the coincidence signal disappearing that way, and then see what remains, whether this remains or just a flat, completely flat angular response remains. So that to me would be the way to probe a system, the pairing in a system. And what is interesting, you could also imagine looking at CDW, the charge density wave, because now the momentum structure would be very, very different. So you could start looking at those phenomena, and based on their angular distribution, distinguish between different forms of pairing. So a particle-particle pairing or a particle-hole type pairing. With this, I think I'm done, and hope that you get some of our excitement that we have these days in UBC with these kind of laser sources. This is actually the photon, the chamber where these photons are being generated. And if you come up with ideas of things that we could try, we would love to hear them. Thanks.